guys, in the previous thing I just completed about the formation of chips in technical material. So how the compressive stress will occur and how the shipments planes will go and how the shear angle will occur. So in that previous class I just explained about you, okay, and what is the feed and how the feed works, and feed is generally mm per revolution, and how much the distance of feed I just told. So each and everything I just told to you, okay. So in this chapter we will just cover a little bit of extra things, okay. So maybe we can just see, can we just go for the problems or not, okay. So one of the other most important thing is you can see about this one. So cutting velocity. So you can see cutting velocity, it is a relative velocity of a cutting tool with respect to workpiece, okay. Cutting velocity, you can see cutting tool with respect to workpiece, okay. This is the rotation and the velocity is moving, so v equal to pi dn, okay. So pi dn divided by 1000 meter per minute and pi dn, so meter per seconds, okay. This thing each and everything is different, okay. Cutting velocity. So next one is chip velocity. You can see chip velocity, it is related velocity to the tool, okay. So it means like chip velocity means you can see the chip moves like this, okay. Like this, the rake angle is there, and here the lip angle, and here the clearance angle is there. It means relief angle. So the chip moves like this. So this is called chip velocity. And the shear velocity, I think you can see according to the shear, it means like this it will be. So this is a shear angle, and here the chip will move. This is the cutting tool, okay. This is again shear. It means shear plane. So in this shear plane, the velocity will move like this, okay. It is called a shear velocity. It is a relative motion between chip and workpiece. You can see this chips moves here. This is the workpiece, okay. Chip and with respect to workpiece, okay. So according to that, okay. So if you just go like this, you can see the entire thing is like this, okay. Okay, I think you can understand. So the chip velocity will be like that, and the shear, it means shear velocity will be like this, and the it means cutting velocity will be like this, okay. So we just put in a basic triangle. So while we just put in the triangle, we will get different answers, okay. So you can see this is equal, this entire thing is chip velocity, this is a cutting velocity, okay, and this is, you can see, this is a shear force, it means shear velocity. So while you are just putting, so what will be this thing, okay. This thing is a shear angle, and this thing is a, suppose for example, this thing is a orthogonal rake angle. So we are just putting each and everything, we just get a required answer, okay. The required answer is this one. So what is the v divided by cos of shear angle minus of orthogonal rake angle equal to vc cutting velocity divided by sin of shear angle equal to vs divided by cos of orthogonal rake angle, okay. This is the main velocity that I just want you to remember, okay. So this most of the question is been asked, okay. V divided by cos of shear angle minus alpha naught, vc divided by sin of pi, vs divided by cos of alpha naught, okay. So next one is shear strain undergone by the chip, okay. Shear strain, okay, not shear stress or not anything. It is shear strain undergone by a chip. You can see this is 0, A, B, okay, each and everything. So you can see shear strain equal to amount of shearing in shear plane divided by perpendicular on shear plane from a point from which the shearing is happened, okay. It is simple case. Shear strain equal to amount of shear occurred in a plane, okay, divided by, it means the distance, okay. That's it, okay. I think you can answer. So you can see this OA is entirely the shear angle, okay. It's amount of shearing, the entire shear thing, okay. Next one, OB is the amount of, it means perpendicular shear plane. You can see this perpendicular shear plane at a point where the shearing occurs, okay. So just remember the formula. So shear angle means shear strain equal to cot shear angle plus of tan of shear angle minus of orthogonal rake angle, okay. I think you can understand. So while you just put for minimum, we need to just differentiate this one, okay. While we are just differentiating, I think so you can see this one entire thing, okay. So what is the main minimum shear strain condition? 2 shear angle minus of alpha naught equal to 90 degree, okay. 2 orthogonal rake angle minus of alpha naught equal to 90 degree. This is the main minimum shear strain, okay. Suppose if theta is 10 degree, you can see that angle, the shear angle will directly 50 degree. So according to this one, you need to just proceed. While we just proceed, you can just get accurate results. So the next thing is I think so you can notice this one, okay. So shear strain is gamma divided, so next one is shear strain rate. Rate is itself, it's gamma divided by time. So rate given, okay, shear strain rate, okay, gamma divided by of time, okay. I think so you can understand. So it means the NT thing, it means how to say, means this OB and OC, this is so okay, it means shear strain divided by delta H, okay, this thing, okay. It means while the video is pressing, I'll just explain you each and everything, okay. So shear strain rate equal to shear velocity divided by thickness of primary shear zone, okay. I think so shear velocity divided by thickness of primary shear zone, okay. Just a simple thing, okay. I think so you can understand. Just one second. Okay. So next thing is cutting velocity. So cutting ratio. So cutting ratio, you can see one is chip thickness ratio, next one is chip reduction ratio. So chip thickness ratio is generally less than 1, but chip reduction ratio is R dash equal greater than 1, okay. Chip thickness ratio and as well as chip cutting ratio. So R is T1 divided by T2, okay. T1 is undeformed chip thickness, okay, undeformed chip thickness, and T2 is chip thickness, okay, deformed chip thickness, okay. I think so you can see this one. So whenever you just take an average T1, so generally we don't do this kind of thing. Generally chip thickness ratio are less than 1 and are greater than 1, okay. Chip thickness ratio as well as chip reduction ratio. So it means TC greater than T, everything I think so you can understand. So this thing, okay. And next other thing is whenever chip, this is also important number. So R equal to T1 by chip thickness ratio, okay. Sine of orthogonal rectangle by cos of orthogonal rectangle minus of back rectangle, okay. So next thing, so R is T1 by T2 equal to length of chip divided by length and VC divided by V, okay. And next one is 1 by, this is the most important number, because in most of the time the question is been asking. So this is the velocity of the chip and this is the velocity of the cutting, this is length of chip and this is the length of the tool workpiece, okay. So this one T1 divided by T2, I think so you can understand, okay. So R equal to T1 divided by T2 equal to LC by L equal to VC by V equal to 1 by H, okay. I think so got the point. So next one, R equal to sine of orthogonal rectangle divided by cos of orthogonal rectangle minus of back rectangle, okay. I think so you can understand. So next one, it means while you just keep on, it means while you just multiply inside and it means what is this one, cos A minus of B, okay. Don't multiply inside, it means cos A minus of B, no, cos A minus B is for that there is a significant formula, okay. So while you just divide by each and everything, you can see while we just convert, it converts to a different format, okay. This is the different format of the angle, okay. I think so you got the point. So this is the most important one. So next one is the tan shear angle equal to R of cos alpha naught divided by 1 minus of R of sin alpha naught, okay. Tan of shear angle R of cos alpha naught divided by 1 minus R of sin alpha. This is also one of the most important one that you just want to say, okay. Whenever if you can see alpha naught, it means back right angle tends to 0. You can see tan of shear angle equal to R, okay. Okay, I think so you can understand. So this formula is continuous. This formula is only for continuous chip flow only, okay. Continuous chip flow only, okay. I think so you can understand. So just a simple thing, no need to complicate yourself. Just remember the formula, each and everything will come in your mind, okay. That's it. So next thing you can see formation of chip in brittle material, okay. Now formation of chip in brittle material whenever a tool comes in contact with the workpiece at the first time. Okay. So whenever the tool comes contact with the brittle for the first time, whether ductile or brittle, a small crack is developed in the workpiece. Yes, small crack is developed, and after the small crack only each and everything is done. So in ductile shearing occurs, okay. In brittle no shearing occurs. So you can see in ductile before thing, ductile shearing occurs, shearing happens, but in brittle no shearing, no shear stress will occur, okay. Direct cutting, okay. So the another thing is you can see in BCC 48 has body centric 48 slip plane is there, and the FCC 12 slip plane is there, HCP hexagonal plug only 3 slip plane is there, okay. You can see number of slip system tells ductile as characters. Number of slip system tells, you can see BCC so much ductile, HCP is lesser ductile, okay. FCC is middle ductile, okay. So FCC is more ductile and this is the 48 maybe the inter packing also we need to see, I think so, okay. So you can see this one. So a slip system equal to slip plane as well as slip direction, okay. Slip plane is a plane of highest atomic density and slip direction means density of the atomic plane where it is being increased. So plastic deformation is ductility, okay, occurs when the atoms slide over each other along the slip system, okay. You can see it is a generally we just taken a system, okay. So you can see in this phase center cubic, phase center you can see in this, okay, and here you check okay. In this each, suppose we just take elements, you can see each and everything is being packed, okay. So here the planar density will be so much higher, but you just take body center cubic. So at the center, so you can see, for example, I just write here means so here the body center. So when you just take vacuum, so at the center it will, I think so you can understand, you can understand. So slip direction, so you can see total number of slip plane is maximum 48 is possible, but it is less than 10. And HCP is little brittle, okay. And you can see in a slip plane is most lengths and there are 12 independent slip planes all easily activated. So you can see no critical resolved shear stress, slip becomes easily even under 2 temperature, okay. And BCC is moderate ductility, okay, and has high potential slip plane but no close packed plane, okay. So that's why it is so much problematic. So here you can see it is no close packed plane, okay. Atoms move, it means atoms move more, so higher CRSS, okay. High, it means CRSS means critical resolved shear stress, okay. So that's why slip only occurs at the high temperature, thermal activation. It means for BCC, for the slip plane to occur, we need high temperature, okay. High temperature, so thermal activation is here, okay. For example, you can see chromium, molybdenum, and HCP is very, so you can see only 3 systems are, so no only twinning or plastic occurs, okay. So I think so you can understand. So close to packed planes and low CRS, okay. And when you just take about the BCC, it has more, okay, that's why, okay. I think so you got the point. So that's why the ductility exists for FCC is more, okay, BCC is less and HCP. So plastic deformation shear really occurs, one atom moves to other atom, yes, definitely. If atoms are more, the movement of one atom to the other atom, yes, very recent. So small energy is needed to move, okay. So FCC is more ductile and less strength less, okay, but strength is less, okay, copper, aluminum and gold. So atoms move easily when load is applied. But you can see BCC is more slip plane, atoms move very difficult, so like a traffic jam, okay. So HCP is total, so brittle, no movement of atoms, so direct shearing occurs, no shearing occurs, direct fracture will occurs, okay. So next thing you can see ductile tool comes contact with the workpiece, so crack and deposition and propagates and it leads to the fracture, and slip plane comes and shear yielding occurs. But in brittle crack happens, hence crack propagates, so but no slip plane, direct no shear yielding will occur, okay. It means cutting and crack are different. So in this crack propagates and chip are formed, every chips are different, okay. So that's why it is called as discontinuous chip, okay. Crack will also go towards the path where the minimum least resistance is there. So okay, so this is the material, means you can see force when applied, the atoms different boundaries will be there as well as the grains are different. So crack propagate easily, release resistance. So you can see A short path at, it means A is a short path at the boundaries and B is a long path. Okay, so B and C requires more times. It means whenever there is a short part, it can discontinue that. So discontinuation different shapes due to grain and boundary of the workpiece, okay. So you can see formation of the small crack. It means small crack and propagation of crack generally brittle. So during machining of a brittle workpiece, material crack develops in the workpiece material just ahead of cutting edge, okay. Crack formation also occurs in ductile material, but immediately shear yielding occurs, so leading to formation of continuous chips, okay. But here that doesn't forms, okay. So you can see the initiated crack propagates before the formation discontinuous. In case of cast iron, is chips are irregular and different chips, okay. In case of ductile material where the strain hardenable discontinuous strip may form and the chips will be regular size. Okay, just a simple thing, no need to confuse yourself, just have in your mind. Okay, so favorable condition of a continuous chip. So continuous chip means definitely it should be ductile, and ductile means it should be low strength and soft and ductile workpiece. So this material undergo shear yielding, propagation of the crack not happening. Okay, propagation of crack does not happen. So on large positive rectangle, you can see large positive rectangle, low wedge action. Okay, this low wedge, so wedge action should be lesser. Okay, where wedge cutting force is more, you can see generally in this wedge cutting force is more, leading to, so whenever the wedge cutting force is more means generally we need brittle material. Okay, so you can see we need light, it means light crack and more shear bend. So phase, so definitely the it should be large, it means the rake angle should be larger. Okay, high cutting speed and shear yielding dominates over crack over shear yielding dominates crack motion, and shear yield equal to v of cos alpha divided by cos of shear angle minus of alpha naught. Okay, continuous chips and mainly shear yielding needed. Okay, if velocity is so much high, shear yielding also high. Okay, I think so. If velocity is so much high, the shear velocity also so much high. Just a formula: shearing takes place more and dominates the crack propagation, and shearing runs this one not needed, and low feed and depth of cut, low feed and low depth of cut. Okay, not greater feed, low feed and low depth of cut. So you can see it means feed is higher, the average thickness also. So it means the average reference also 20 be so much high. So if width of the cut is higher, then depth of cut is also higher. Okay, I think so. Can so crack domination dominates. It means hence crack propagation dominates the shear yielding. Okay, Vs level delta H. Okay. So next one, favorable condition for discontinuous chips. Okay, hard and brittle material. Okay, discontinuous. Okay, hard and brittle workpiece material. Crack propagation dominates and smaller rake angle minus rake angle. Okay, so leads to larger bending action and low cutting speed. And it means whenever it is low cutting speed, definitely the shear angle also, the shear velocity also will be lower. Okay, then crack dominance. So and here the larger feed and larger depth of it is we needed. So no cutting fluid is required because it is discontinuous chip. Okay. So you can see whenever the rake angle is small, you can see the cutting force is so much high. Okay, rake angle is small, the cutting force high, and heat also so much high and sticks. Okay, while mixing soft and ductile material, the contact within the workpiece highest stress. Okay, so high temperature occur. So soft and ductile material at high temperature, adhesive portion increases. So definitely the cutting will occur. Okay, and as well as the built-up edge also will definitely occur. Okay, so this is a basic thing you just remembered in mind, and later on I'll just explain each and everything in a detailed video format. Okay, it tends to stick towards the tool and wedging soft and ductile and ECC, and if high temperature given, hard and brittle will remain difficult. Okay, so next one is build-up edge. Build-up edge now form, it means the cutting action takes place by covering the workpiece material. Okay, as we do machining, the build-up edge increases and more workpiece material sticks towards the tool above. Okay, so you can see this is the build-up edge, and the build-up edge increases, and I think so you can see instead of being a positive rectangle, it tends to become a negative rectangle. So during negative rectangle, the stress concentration is so much higher in the tip, and it fails so much easily. Okay, so okay, so you can see build up thing increases, so it tends to negative rectangle. So tool geometry effectively jam, it means gently changes. So wedging action is greater and the crack happens and force also increases. Okay, so next one, build up edge. So while cutting stresses, it means while cutting stresses increases, and at one point the stress will become more than the cutting of the more than the strength of a material, so leading to crack of build up edge. Okay, so you can see it means it increases and it leads to pickup of materials of tool material. Okay, so process ends and the process again starts. So cutting, so it leads to so much probability thing. Okay, so due to build up formation, tool life decreases. Okay, it means at the first time, it means first the tool life increases, and while build-up is formed, because while the build-up edge is formed, so definitely it means it and it means withstand lot of stress, but later on the tool life decreases. So build-up formation, so definitely positive rectangle should be and soft and ductile and smaller rectangle, and cutting speed must be medium. Okay, if cutting speed is low, then the workpiece sticks to the tool increases, and if cutting speed is high, we don't give time to stick. Okay, I think so can understand. So just a simple thing, and you can see next one, feed and depth of cut is medium, and if more material removed means no heat interaction occurs, and chipping, so it is not needed. Okay, so good if less material removed and heat occurs. Okay, if less material heat occurs, but this less material does not cover the tool surface. So feed and depth of cut is medium. Okay, inadequate and absence of cutting fluid. So during mission of the soft and ductile workpiece, a large amount of stress and heat is generated in the workpiece. Okay, so very high temperature at the cutting edge you can workpiece. At very high temperature, two, it means a very clean surface, and addition is definitely start. So workpiece starts to adjust to the cutting edge, similar to the welding action of the formation build-up. So while continual machining process, build-up edges increases, result to change in the tool. Okay, this leads to force increases. So since the stress occurred by the cutting force goes beyond the strength, the build-up edge formation, the fragment within the towards the request VSR. Okay, deteriorate surface finish. So that's it means just a simple thing. And you can see favorable condition, we see all we change and we reduce the build-up edge. Even though it means warmed, it means use ceramic, it means cement. Cement means ceramic plus a material tool. So here no shrinking action, so due to the powder metallurgy. Okay, so build-up edge formation can be avoided by increasing the rake angle. Okay, and cutting speed. Okay, and decreasing the feed and the perfect, using sufficient cutting fluid, and using a special tool called cement. Okay, cement. Okay, CERMET, cement. So these are the next two things. Okay, cutting orthogonal and oblique. Orthogonal is 2D and oblique is 3D. Okay.